Hello everybody, I'm back again to work another equilibrium example where we calculate the composition or the concentration of the system at equilibrium. I try to pick an example with some different aspects to it, different from prior videos. So I picked a realistic example. It's actually kind of similar to problems I've asked on exams before, just in terms of just general form. We have a problem here where we have H2 gas and I2 gas going back and forth, reversible reaction to 2. Already I realize I need my sock eraser. It goes back and forth to 2HI. So we have this reaction, it's all in the gas phase. We're told that, let's see here, that at a certain temperature, that Kc is equal to 50. And we're told that at that same temperature, we have a system prepared. Whether we prepared or we find it like this is irrelevant, but the system is described at a certain point in time, having H2 equal I2 molar concentrations of 0.100 molar, and has also HI at 1.00 molar. So the first thing to do, we'll call it the dice method. I like that. So we have this direction step first. So the first thing I would do is I write what we call Q sub C, I guess. And it's products, HI, don't forget to square the HI. And then we've got H2 and I2 in the denominator. And we plug in these initial values. We have 1, I'll write it in formally squared. Of course, 1 squared is just 1. And then we have a 0.1 for each one of these. So we have 0.100 squared. Don't forget that. And that's equal to 100. That's 100. So in this particular case, unlike prior examples, this case Q is greater than K because K is 50. So the big implication here, and this is like a really important step, is that when Q is greater than K, we head left to products. We're heading left in the reaction. That sets us up. That's an important step. That's the kind of thing on an exam that to me is a bigger deal than if you get the subsequent algebra correct. I'd be like, wow, okay, you can do a quadratic equation or whatever, but you can't set up, you did it right, but you set the wrong problem up. This is like a critical step. That's almost like if you can't write this down and determine that to me is a lot bigger diagnostic of not understanding the material than making an algebra mistake. So at this point we can set up an ICE table, H2, I2, and HI. And we take note of the 2 here. And this is all going to be in molarities. I'm not going to write that in every time. So we have the initial step. We've got, what do we say? We got 0.10 for these 2 species, the H2 and the I2. And then we have for the HI 1 molar. The change step this is critical here. Now we're going to the left, right? So we're picking up an X and an X for these 2 species. Every time we pick up an H2, we've consumed 2 HI. And same thing, we pick up an I2, we've used 2 HI. So here, this is a minus 2x. This step right here is probably a problematic step for a lot of people that I've observed in the past. So I try to, as I learn these things that are problems for people, my learning experience in here is mostly figuring out what people have a hard time with and trying to adjust my emphasis and teaching strategies around that over time. And I find what people have a hard time with changes over time. So now we bring it on down. 1.0 plus x, 1.100 plus x, and then we have 1.00 minus 2x. A lot of times at this step as well, I notice that people have it good here and they just write minus x. Now that might be a typo. That might be a real, not a conceptual flub, but more of a math flub. And so let's, again, Q and K have the same form, so we can write KC is this. And it's always good to write this step out because a lot of people somewhere in here do like a mental step and they forget to square things. I find that. And so now what we do is we plug in the things in terms of the algebra into this framework, and we've got 1.00 minus 2x squared, and then we've got 0.100, these are the same, plus x squared is equal to, what do we say it was, 50. That's what the value is, 50. Looks good. Now, first point, 50 is a big number. We cannot do no small x approximation here. That's not when to use it. This is definitely a lot bigger than 10 to the minus 4. It's like 5 orders of magnitude bigger almost. So it's not appropriate to use it, not even close. This can be done out fully quadratically, but when you inspect the problem, always remember, particularly on a test, we're often trying to present conceptual testing, at least I am, and I would consider this a good practice for most people who design tests is, the algebra is important, but what's more important in a chemistry course is understanding the chemistry. So we often pick problem types that the math isn't the worst ever. That's how I do it, and I teach some rather mathematical courses like thermo, so I don't try to pick the biggest cruncher in terms of math. I try to pick problems that accentuate concept. So here, you could do it all out quadratically, square, separate, get things in the form of x squared plus x and plus a constant form. But what you see here by inspection, this is a perfect square. So review your math with polynomials if you're forgetful of that term, but what you can do is go back, and unfortunately there will be things that have to be erased here when I get going, and what you can do here readily is just take the square root of both sides. So when you take the square root of 1.00 minus 2x, and then you hit squared. I'm doing it out. Hopefully you can see this readily. Just to make sure everybody knows, this is the same as saying, there's a lot of ones here. We have that, and don't forget, this is going to be a plus or minus square root of 50. There's two roots here. One of them will be valid. So that's the setup of the math. So let's do it out. I have to erase stuff. We can rewrite it back at the end. So we have to have some space for the math. Let's see here. So we've got this setup now. I'm going to start with the positive root first. So the positive root, just square root of 50, or positive square root of 50, you want to write it out. So let's set it up. We have this expression, let's cross multiply. So on this side we're going to have 1.0 minus 2x is equal to, and then we're going to have 0.100 plus x times the square root of 50, and that's going to be equal to 0.100 times square root of 50 plus x, I'll put the x in the front, square root of 50. So we have that, and that's going to be equal to that. Get all your x's on one side. The way I decided to line it up is x square root of 50 plus 2x. So I'm pulling that over, and then I'm pulling the other one to the other side. Doesn't make a difference as long as you're consistent. 1.00 minus 0.100 times square root of 50. So now x is going to be equal to we have that, and then we have factored, so we're going to have square root of 50 plus 2 in the denominator. Make sure it's correct. Easy to make a typographical error on the board. Do the math out on your calculator. I'm going to keep it to some extra sig figs, just 2, 2, 3. Molar, again, I'm just keeping extra sig figs on there to have things to work with on my calculator. I just keep all the numbers running. So that's x. So you go back to the equilibrium table. Unfortunately, we have the H2 and the I2 and the HI. These two are in the form of, what do we have? These were in the form of 0.100 molar plus x, and this was in the form of 1.00 minus 2x, and this would be molarity, right? So let's plug them in. And so what we'll do is for concentration of H2, it's going to be the same as I2. There's no reason to do this twice unless you just like doing math. We got 0.100 molar plus, that really limits how many sig figs we have. 3,223 molar. We have that. So that's going to give us, let's see here, we got 0.32, we got a 0.1, we got, that equals 0.13223 molar, more sig figs than we justified. In terms of the answer, this would be 0.132 molar. That would be the concentrations of I2 and H2. If we're correct, those would be, for HI, we've got 1.00 molar minus 2 times this number, 0.03223. This is, I'll put a little asterisk here. A lot of times people put that as the answer. That's not the answer. The answer is what you have to do the mathematical operations in that equilibrium step on your table, or whatever your equivalent algebraic representation is. Let me see what that is. That ends up being 0.93554 molar. That's too many sig figs to the answer the problem would want. That would be HI is equal to 0.94 molar, because we're limited to 2 places behind the decimal in this process from initial. I usually have an exam, I would say report the numbers to a certain number of sig figs. Let's check it out. So, does this make sense? And we only did one root. Let's do a check. Let's plug it back in to Kc is equal to Hi squared H2 I2. I'm going to use the more sig fig in numbers. So Hi is going to be 0.93554 squared, and then we have the two same values down here squared for the H2 and I2. That's going to be 0.13223 squared, which is equal to approximately 50. It was 50 point something. So that's good. That's our initial, that's what we started out with. That's your check. So if you came out with 99, 7, 10 to the minus 4, whatever it is, you know you made a mistake here. Now, it could be two things: is that you made a mistake or you picked the wrong route. So what about the other case? And this is if you're on an exam, this is clearly the right root. You end up with the same equilibrium constant that they gave you at the end. So you can always check your answer. Sometimes I see people give wild, wacky answers and they're leaving like an hour early on exams. And like, I'm sitting there like, wow, like you're way off. Why didn't you check the equilibrium constant? This is a 25-point problem. You know, you give me answers, they look weird, and you didn't check your answer. So this is, take a look at the board. That's just the math. That's actually not the most important problem. The setup is the most important part. So let's do the negative root. I'm just going to sketch out some of the reasons why it is. You can go through and confirm all the algebra. So this was a perfect square problem. Again, if you want to do the full quadratic out, you can. You're going to come out with the same answers, but it's a lot longer. In that case, negative root. So we're doing the negative root now. 1 minus 2x over 0.100 plus x is equal to negative square root of 50. That's the second root. And so do it out. Do it out. You get to the step where you have x is equal to negative 0.100 square root of 50 minus a lot of negatives here, 100, 50 minus 2, and this is going to be a negative number, negative 0.3366. I'll keep some extra sig figs on here. That's the molarity. Think about it. So, for example, H2 equals I2 equilibrium concentrations, this is just for example, is 0.100 plus x. This is all in molarity, so this is going to be, when you do the math out, that's going to be 0.100 molar minus, because x is a minus number here. Don't minus of a minus, it's a minus as is, 3366 molar. So it ends up, whatever it is, it's a lesser number. It ends up being 0. Well, that's going to be a negative number, right? So that's a negative number. In this particular case, it's negative 0.2366. That doesn't make any physical sense for one reason, even if it was a lesser number, because these ones are building up, but instead we're going down. And in fact, we went so down so far, we're a negative number. So it makes no physical sense. There is no logic to it. It's a mathematical artifact. It's correct mathematically. It's a solution to an equation, but there's only one root that will be a physically reasonable solution to this, and that is, people say, well, how do I memorize this? I'm like, what's the hack here? What's the cheat code? Like, whatever. And I'm like, there is none. You have to use physical sense, understanding. In this particular case, these are building up. The reaction is shifting to the left. These are the reactants, H2 plus I2 going to H2HI, right? And we're shifting this way. The concentrations of these has to increase, even if this ended up being a positive number at the end, but it was smaller. Let's say instead of 0.1, it ended up being 0.03 or 0.02. It still doesn't make sense physically because they're supposed to be building up. And so you can knock this out several different ways. The first answer I chose happened to be correct, but sometimes you might choose the wrong root. There's no shame in that, but you'll see like this doesn't make sense. Try the other root. So this example showed a couple different things. A, it showed we checked Q and K versus K, and we determined the direction first. And in this case, unlike a lot of the canned problems in many books that tend to always be going to the right, this one ended up going to the left. Set your algebra up accordingly. Rule, I would say, big observation too. Don't overuse the small x approximation. Here, K was 50, way big, too big by many orders of magnitude. To use the small x approximation, you'll get a really shoddy answer that may not make physical sense. Number 3 is look for easy but legit ways out on your math, particularly on exams. And so in this particular case, the easy way out was that it was a perfect square, and you just take the square root of both sides. And so that's easy enough, and you should be able to see that by inspection. Is that a setup type of problem? Yeah, it's a setup type of problem because I don't want you to spend an hour just doing a quadratic equation and struggling and me having to do, decipher that. This allows me to see if you know a lot of common sense things. The next big observation here, with quadratic equations in general, whether it be from a perfect square or not, you end up with two roots and only one of them is physically realistic. And so you have to have the understanding of what's going on to make the right choice. And I guess the final rule is when you get said and done, you get your tentatively correct concentrations or partial pressures. There's no excuse to say, wow, it's a mystery to me if I made a mistake. Is you can definitely tell if you made a mistake if you go back and you plug them into the law of mass action, K equals, and you don't get a reasonably close value to what you started with, then you've probably made a problem somewhere. And by reasonably close, I mean if your answer is, if your theoretical KC value is, let's say, 50 and you get 49.8, this is a problem that involves a lot of math steps. To me, that's a totally valid answer. Your the two sig figures, you're 50, and that might be all you're justified for. Sometimes students really come up to me and say, I'm, like for a problem like this, I'm 49.97, is that 50? I'm like, yeah, you're starting out with two sig figs here. I mean, come on. So, at any rate, this is a good problem, very representative of a test type question. Do not say, well, they're always going to go to the left in this framework, go to the right. There could be cases where you're at equilibrium on a qualitative question where that could be like we're at equilibrium. So on that note, we got one or two more videos for this chapter, unless I add some extra stuff. And then we'll move on to, I believe after this, we're going to do acids and bases. So on that note, have a great day. Maybe I'll make another video.